Okay, right, please. So, last week's lectures we introduced the idea of the general linear model, which we can write in matrix form like this. So we've got our data points, which we write as vector y. We have x, which is a design matrix with the entries in x are the coefficients for the model. Beta is a vector of unknown parameters, and epsilon here is the random part of the model. Okay? So the x beta part here is called the linear predictor for known design matrix x and unknown parameter vector beta. This gives us our mean that we expect our observations to have, and then this epsilon term is the random part of the model. Okay, so on Friday's lecture I got to the statement of this theorem that the least squares estimator for beta was what we'll call beta hat, which can be written, again in matrix form, as a slightly complicated matrix which involves x multiplied, this is called matrix multiplication, by the vector y. So it says on the slide this is proved by differentiating with respect to beta I and a bit of linear algebra. Let me just show you how you can get an idea of how to do this. Okay, so what we want, okay, we want to minimise the residual sum of the squares. And the residual sum of the squares is the sum of all data points. So I'm going to use j as my summation index here because I'm going to want to differentiate with respect to beta I. So I don't want to confuse those two indices. There are n data points, so it's a sum from 1 to n. Okay, and the residual, remember, is the difference between the observed value, which is yj, for the jth observation, and the value of the linear predictor that will be given by a particular choice of the betas. So here we have x beta, and we want the jth element of that, and it's residual sum of squares, so we need to square that. Okay, so let's take the partial derivative with respect to beta r. Okay, so if we differentiate the residual sum of squares with respect to beta I, that's just going to be derivative with respect to beta I of that sum. Now, before I actually do the differentiation, x beta there is a matrix product. So to actually explain what's going on in the differentiation, it's going to be helpful to write that matrix product out as a sum. So we've got the sum equals 1 to n, yj as before, and now as I say I want to write that matrix product, we want the j element of the matrix product there we want it as a sum. So sum. I'm going to write it as a sum from k equals 0 to p minus 1. Remember that p is our notation for the number of coefficients here, so the number of entries in beta. And that's also the number of columns of the design matrix X. So it's the number of things in our matrix for each one of our observations. And usually we write beta 0 for the term corresponding to the intercept. So that means we've got p columns in total, they're going to be indexed from 0 to p minus 1. So that's why the sum is from 0 to p minus 1. Okay, and then what's in there is just xjk times beta k. So taking the sum of this gives us a jth element of our matrix product. Okay, and we need to square that. Now, we want to differentiate that with respect to beta I. Now, the only case where beta I is going to come in the the only case where beta I is going to come in here is in the case of the sums where k is equal to I. Okay, so if you differentiate this, you're going to get a term which comes from this bit here, which, because you've got a minus times xjk, you're only going to get it in the case where k is equal to I, because that's the only case where we're differentiating with respect to beta I, so we need I here to actually get anything at all from that sum. So we end up with a 2, which comes from the fact we're differentiating the square. Sum from j equals 1 to n. We get minus xji, which comes from this term, that minus sign, and as I said, k equals I there, times yj minus this sum again. Okay, so we're almost there, because we can rewrite that twice the sum from j equals 1 to n, the xji again, so I've now lost the minus sign, so I'm going to need to subtract things inside. So let's, of course, start off with that term which has the sum from k equals 0 to p minus 1. Okay, and then we want this term which had the yj. That's now going to have a minus sign. So we've got twice the sum of j equals 1 to n of x, j, I, y, j. Okay, so let's move on to the board. So, these sums here now look a lot like matrix products. Okay, so, and in both cases, the term that the suffix that we're seeing on its own is I, so these are actually going to be the ith elements of matrix products. Okay, so it's ith element of matrix product. So let's look at the first one. So we've got 2 here. Now note that we've got xji here. Now that looks like it's the wrong way round, because we're going to be summing over j. The matrix product would normally have the thing we're summing over second in the first variable. So that means that the I and j are the wrong way round here, means that we've really got x transpose. So the xji corresponds to x transpose. The xjk just corresponds to x. They're now the right way round because we're summing the second thing we want to have the thing we're summing over first. So x transpose x times the vector beta minus, and then this one again, xji indicates x transpose y. Okay? So we want the ith element to be the same for all I. We want this to be equal to 0. Okay? Because we're differentiating to try to find a minimum. Okay, so the only stationary point of the function we're trying to minimize is if our beta, so we want this x transpose x times beta to be equal to x transpose times y. So the way to do that is to take x transpose x, take the inverse, so we can take it over to the other side, and then we still have x transpose x to the minus 1 times x transpose times y. Okay, so as I said, we're differentiating with respect to beta I. That was the first thing I did, and then a little bit of linear algebra to get to the final answer. Okay. So I now want to move on to section 1.4 in the notes. Section 1.4 is called Fitting Linear Models in R. So when I do this, I'm going to use a particular example data set, which I'll introduce in a minute. I'll actually show you the numbers. One thing I'll say is I will try, when I do things in R, to put the code that I use on mole at some point after the lecture, so that you can try it for yourself without risking typos as you copy from the lecture notes. Okay, so let's have a look at the data set. So the data set has 17 tractors. These tractors are of different ages, and the data point that we're interested in, what we're interested in trying to predict based on the age, is the maintenance costs of the tractor. So it makes sense if you think about it, that an older tractor is likely to cost more to maintain. Okay, so here's the data. So say there are 17 data points. So the ages range from half a year to 6 years. And we've got the maintenance costs, which are in pounds, for 6 months given here. So we can see, if you just look at the numbers, that indeed we have smaller maintenance costs for these younger tractors here, and tend to have larger ones for the older tractors down here, but there are some which maybe don't fit in that well, so this is only 1 year old, but it's got quite a lot higher maintenance costs than the other ones around it, and that's probably not that surprising that we get that sort of phenomenon in a real data set of this type. Okay, so one question we might ask is a simple straight line relationship between the age of the tractor and the maintenance costs a good model? Okay, so that's actually a simple linear regression. Later on in this section we will actually do a few more complicated things with this data set, but for now, I'm just going to focus on the simple linear regression. So P is just going to be equal to 2. Our only explanatory variable is going to be age, so our design matrix will just have 2 columns, one of which will be a column of 1s, and the other one will be the ages of the tractors. Okay? And 2 parameters to estimate: the gradient of the line and its intercept with the y-axis. Okay, so on the next slide I'm going to show you a scatter plot. The scatter plot is actually going to have some things which I'm going to tell you about later on. And I'll indeed show you how the scatter plot can be made in R. And it does indeed show, which is not surprising from the numbers on the previous slide, that the maintenance cost tends to increase with age. Okay, so here's the picture. It's in the notes as well. Might be slightly clearer in the notes. So the little crosses like this one are the actual data points. So age on the x-axis, maintenance cost on the y-axis. And we can see a straight line fit. You'll see some crosses. Those are the fitted values in R's estimated model. So they will make sense in a minute. So this graph was indeed produced in R using the code I'm about to describe. Okay. So the main function for linear models in R is lm. Okay, so here's an example command using the function lm. So to do this, we're going to need to have the tractor data already available to R as a data set. So otherwise data equals tractor.data here will give an error. The columns in that data set are labelled mate and age. And the tilde here is saying that everything on the left, so the mate, is the thing that we're trying to model the outcome of, so the maintenance cost in this case. And the age is what we're trying to make our regressor variable, so the things we're hoping will explain the variation in the things to the left of the tilde. So the tilde here separates the things that we're trying to predict from the things that we're trying to use to predict them. Okay? And the way that this lm function in R works is that it produces an R object which has information about the fitting process of the linear model in it. So if you just type lm and something like this after it, nothing will happen except that, well, nothing that you can see will happen. What you need to do is to give it a name, and here we're giving it the name tractor.linear.lm. Okay? Once you've done this, you'll be able to do things with this R object, tractor.linear.lm. Okay, so that tells R to fit this simple linear regression model. So although we haven't explicitly said that we're going to fit an intercept in the R command, R assumes that we are unless we tell it otherwise. Later on we will see how we can tell it otherwise if we want to, but you don't usually. And age here is the x term. So R is being told here to fit this simple linear regression model that the maintenance cost is intercept plus the gradient beta 1 times the age plus some random term epsilon I. Okay, so as I said, you have to have, R has to know about this dataset tractor.data. This command that I've put at the bottom of the page is one way of telling R about it. So if the tractor data is available to R, if it's in the folder where your R is in your R working directory, then this command will actually give it the name tractor.data, and then you'll be able to use that as a data set. Okay. So the fitted values then are, which are in the plots that I showed you before. So that was the plot here. So note that the fitted values appear already in the plot. Okay, so those then are in a straight line, and they're of this form beta 0 hat plus beta 1 hat xi. So beta 0 hat and beta 1 hat here are our estimates of beta 0 and beta 1. Remember, hat always means the estimate of. It's pretty much universal use of hat in statistics. Okay? So it turns out that we can add the line that R fits to the plot using a couple of simple commands. So one of them is this command, this AB line. So that adds the line, and R is able to work out what the line is just from the object tractor.linear.lm that we created. And this second line here, using the function points, so points adds points to a plot which already exists. So the age here is the age from the tractor data set, and tractor.linear.lm $fitted extracts the fitted values in the model from the tractor.linear.lm object. Okay, so this variable here, tractor.linear.lm $fitted, that extracts the fitted values from the object. So a $sign in R tends to mean that you've got some object which has lots of pieces of information in it, and the thing after the dollar extracts a particular piece of information from the object. PCH equals 4 on the end is just telling R what sort of point to plot. So this is just a thing which changes the appearance of the points which we're plotting. Okay, so the line we get using that is shown in the plot that I showed you a couple of slides back. Okay, so let's look at some of the numerical output that R actually creates when you run that function ln. So, a simple thing you can do is to just type the name of the object that it created, so the name that you gave the object when you ran the model, into R. Just the command line. So you just, having run what we had before, you just run tractor.linear.lm. Okay? Now if you run that, you get some fairly basic output. So that's just saying that we've run the command. So the first thing this gives you is the call, which means that the model that you asked R to fit. So this formula equals mate tilde age. That's just a slightly expanded version of what we entered into R when we ran the lm command in the first place. Okay? So this is just essentially what we did to run the model. So there's no more information in the call line that we don't already know. And then it gives us the estimated coefficients. So R is saying that the estimated intercept is 323.6, and the estimated, what it says here, age, of course it doesn't mean the estimated age, it means estimated coefficient of age, so it means it's estimated beta 1. Okay, so it means it's beta 1 hat. So this is beta 0 hat, and this is beta 1 hat. Okay, so as I said, this gives the estimates of the beta hat parameters, and it hasn't told us anything else. But this is probably the first bit of information we're looking for when we fit a model like that, is what are the actual estimates of parameters that we get from the model. So interpretation here, so beta 1 hat, the second one, so this gives the estimate of the gradient of the fitted line. So that tells us how much we expect the maintenance costs to increase for each extra year of age. Okay? Now, as I said, this is expected. It's emphasised on the slide that it's expected. So, there's the error term in the model, the epsilon bit, so that tells us also the random fluctuations around the expected value that we get for the actual maintenance costs of any particular tractor. Okay. And similarly, the expected value of the intercept, ours estimate is 323.6, so that's telling you the sort of baseline maintenance costs of a tractor before you take into account its age, essentially the maintenance costs for a tractor whose age is 0. Okay, so that was a pretty minimal summary of what R had fitted in the model. Now it turns out that the command summary, so applying this summary to, again, the name that we gave the R object that was created when we ran the model, gives more detailed output. Okay, it might seem a little bit odd that just typing the name of the object itself in gives a minimal summary, and summary gives you more data, but that's how it works. Okay, so I'm going to go through what we get, and this won't all be on one slide because R actually produces quite a lot of information when you run the summary command. So I'm going to show you what R produces. So again, it repeats the call that you used when you ran the function. Then it gives you some information about the residuals. Remember that the residuals are the differences between the actual data values, the observed data values, and the fitted values in the model. So R gives you some summary statistics. So the biggest residual was 539.8. The smallest residual was minus 355.49, and it also gives you the median, which is a little bit less than 0, and the upper and lower quartiles of the residuals. So here's the upper quartile, and here's the lower quartile. Now we'll see as we go through the course that residuals, looking at the residuals and their distribution, can be informative in whether the model is actually a good fit. And I'll say a little bit more about this in a minute. However, I should point out that we've only got 17 data points here. 17 data points isn't really very many, and it's a little bit hard to make definitive conclusions about a poor fit from just 17 data points. Okay, it also gives us rather more detail about the coefficients and the fitting of them. So here we have a row for each coefficient that it's tried to fit, so each beta hat. So the first row is for the intercept coefficient, which was beta hat 0, and the second row is for the age coefficient, beta hat 1. So for each one, it's giving us the estimate. So the first entry in the row is the estimate, and we've already seen those. The next one is the standard error. Okay, so this gives you an idea of how much confidence R has in those estimates, and we will see how that is calculated as we go through this section. Okay, so the standard error for the age coefficient is about 35. The standard error for the intercept is quite a bit bigger, at nearly 150. Now it also gives you some things which look like the outcome of t-tests. It gives you a t-value and it gives you a p-value. Okay, so probability greater than mod t here is a p-value for a t-test. Now we'll talk a little bit more about these tests in, I think it's section 1.10 later on in the course, but you can actually see that these are basically calculated by taking estimates and dividing them by the standard error, and then these are just by comparing with a specific t distribution. And it turns out that for 17 data points and p equals 2, so 2 columns in the design matrix, the number of degrees of freedom for the t distribution is 15. Okay, that isn't yet this. R gives you these significance codes after it does the tests. So you may remember that there tends to be a convention that results are significant of hypothesis tests if the p-value is less than 0.05. This is just a convention, but the information in R is compatible with it. If the p-value is less than 0.05, so this is conventionally a significant result, you get a star. So you see the top one, the p-value is just below 0.05, so we get a star. There's then another threshold of 0.01, which is included, and below that we get a double star, which is what we've got here. We don't see it in this example, but if we'd got a p-value below 0.001, we would get 3 stars. If the p-value is close to significant in the conventional sense, but not quite, so between 0.05 and 0.1, you'll get a dot. So if you want to think in terms of the conventional significance level of 0.05, this means nearly but not quite significant, this means it is significant, and then these are stronger results over here. Okay, so it also gives us some more information, and we'll see what this more information really means as we go further through the course. So we've got the residual standard error. It now tells us that there are 15 degrees of freedom, and there are some things here called multiple r squared and adjusted r squared. As I say, we will see what those mean later on. There's something which looks like the outcome of another statistical test. It gives an F statistic, so that relates to the F distribution, which some of you may have seen before, and again it gives a p-value, and it turns out that this p-value here is exactly the same as the one that it gave in the t-test age, and there are good reasons for that in the way that R is interpreting the information. Okay, so, as I said, one of the first things it gives is descriptive statistics of the residuals. So for a good fit, remember that the residuals are approximately normally distributed. Okay? In our model, we assume that the epsilons here would have a normal distribution, and that means that our residuals should also have an approximately normal distribution. So we want these to look like they're from a normal distribution. So, in particular, the normal distribution is symmetric. So for a good fit, the median should be close to 0. Also, coming from wanting symmetry, the minimum and the maximum should be about the same in absolute value. So the minimum should be about minus the maximum. Okay? This is also saying that our distribution isn't too wild. If we have a wild, heavy-tailed type of distribution, then you might well get an extreme value in one tail, but not in the other. So you might get a big maximum, but a minimum not too far from 0. Also looking for symmetry, the two quartiles, the upper and lower quartile, they should have, again, approximately the same absolute value. So Q1 should be approximately minus Q3. Okay, so if these don't appear to be the case, then that may indicate that there's a problem with the model. So in particular, they could be positively or negatively skewed. However, as I said earlier, if your data set is small, then it's not really that easy to tell. So you might get something which might look alarming, but because the data set is actually quite small, it isn't really. It was just a bit of bad luck. So if I go back to the actual things we've got, here we are, the residuals, so we can see here, well, the median is a little bit less than 0, but on the overall scale of the things we're seeing in this data set, it's not too bad. I mean, it's going from about minus 350 to a bit over 500. Zeros fairly middling in that. Maximum is a bit bigger than the minimum in absolute value. The quartiles, not too far apart in absolute value, but the first quartile is a little further from 0. With 17 data points, there's probably nothing really alarming here, but the fact that the maximum is so big might be slightly alarming, but I don't think it's very alarming with only 17 data points. Okay, so that's how far we've got. Okay, so now I'm going to move on to the next section of the notes, which is section 1.5, which is about properties of the least squares estimators. So what we're saying in this section is that from the assumptions that we've made, some facts about linear algebra and some facts about the way that distributions vary under transformations, we can get some information about the distributions of our estimators. Okay? So, I should mention here that on MOL, there is a document which is called an appendix. The appendix contains various information about linear algebra, and it also contains some information about transformations of random variables and how the mean and variance, and for multivariate distributions, the mean vector and the covariance matrix are affected by transforming linear transformations of random variables. So in this section, we're going to be referring quite a bit to results which are in that appendix. Okay, so first of all, let's think about the actual mean and variance of the estimators. So this actually doesn't refer to the estimators at all, it refers to the data values y. So our assumption was that y was x beta plus epsilon. Epsilon had been 0, so that means that the mean vector of the y's must be given by x beta. Okay? And the variance of the y's, again coming from our assumptions, is just sigma squared times the n-dimensional identity matrix, because we assumed that the epsilons had variance sigma squared and were independent of each other. Okay, that implies that this is the form of the covariance matrix for the y's. Okay. And we've also got the further information. These have a multivariate normal distribution, so that means the y's also have a multivariate normal distribution in our model. Okay, so that's a starting point. The other thing that we're going to need is the formula, which I was proving on these boards here, for the least squares estimators in terms of y. Okay, so we saw that beta hat can be written as this x transpose x to the minus 1 times x transpose times the vector y of the data points. Okay, so beta hat can be written as a linear transformation of y. You take the data y and you multiply them on the left by that matrix. So x transpose x to the minus 1 times x transpose is of course a single matrix here. So we're multiplying y on the left by that matrix. Now, if you take a linear transformation of a random vector, something like this, then to get the mean of the transformed random vector, you apply exactly the same linear transformation to the original mean as you applied to the variable. Okay? So, the expectation of beta hat, the mean vector, is going to be that matrix that we've just written down over here, x transpose x minus 1 times x transpose, times the mean of y, and the mean of y is x beta. Okay, so x beta here comes from the mean vector of y. So that's from the expectation of y from the previous slide. Right. Simple linear algebra here. We've got x transpose x and x transpose x to the minus 1. Okay, so we've got the inverse of the matrix times the original matrix itself. So that is going to give us the identity matrix, and that means it does nothing. So in fact, the expectation of beta hat is beta. So that means, in statistical terminology, that beta hat is an unbiased estimator for beta. If you start off with the if we start off with the true model involving beta, then the estimates we get from running the model will be unbiased. Their mean values will be the true values. Okay? So beta hat turns out to be an unbiased estimator of beta. This is something which is often regarded as a good criterion for an estimator to satisfy. Okay, we can do something similar with the variance. Again here, we're going to need to appeal to the theory of what happens when we take a linear transformation of a random vector and what happens to the covariance matrix. Okay, so beta hat is equal to this matrix that we've mentioned before with the x's and x transposes in it, times y. Now, the theory of transformations tells you that if you take the variance of something with a transformation like this, you get the original covariance matrix of the y's in the middle. On the right, you get the thing that you've got you're doing the transformation by, and on the left, you get its transpose. So if we apply that in this case, okay, we've got the transpose on the right. Okay, so here we've got x transpose x to the minus 1 times x transpose. We take the transpose of that and put it on the right. We've got the variance, covariance matrix of the original y's, which we put in the middle, and the matrix that we're doing the transformation by again on the left. Sorry, I think I said left and right the wrong way round the first time. Okay, so the transforming matrix on the left, the covariance matrix here, and the transforming matrix, but it's transposed again on the right. So this again comes from the general theory of how covariance matrices change under linear transformation. Okay, so the covariance matrix of the y's is sigma squared times the n-dimensional identity matrix. Okay, so we can just replace that variance of y in the middle by sigma squared times the identity matrix. Okay, and once we do that, we're going to be able to do quite a lot of cancellation. So we've got an x transpose x to the minus 1 here, and then the sigma squared we can take out to the front, so we don't need to worry about that. Identities disappear in matrix multiplication. So we've effectively got x transpose x in the middle again. And then we've got the inverse X transpose X at the end. Okay? And that comes from the fact that when you take the transpose here, you swap the order of the terms in the inside. Okay? So the X transpose X's are going to cancel with one of the inverses. Doesn't matter which one. And so we end up with sigma squared times X transpose X to the minus 1. So that's actually the formula for the variance of the estimators. Okay. We can do some more things with the residuals. So the residuals, remember, are the differences between the observed values, the y's, and the fitted values, which are the x beta hats. And we can put them all in a vector, which we call E. And so E is defined to be y, the vector of the observed values, minus x beta hat, the vector of the fitted values. Now we know that x beta hat is x tx to the minus 1 times x transpose times y. So we can rewrite that beta hat in the first form there to get x tx to the minus 1 x transpose y here. Okay, so now both of those involve y. Both the first term here and the second term here involve y. So, if we invent a new matrix M, M is simply going to be the n-dimensional identity matrix minus the stuff we've got here, with the